Yes, he's going over this one. And yes, when grading comes along on Friday, I will be trying to grade this particular one. Well, questions 1 and 2. Because I believe those are going to be, well, if you sum them together, they're worth 55 points between the two. So this right here is organic chemistry, mastering these reactions right here. Now, I'm not going to spend too much time on some of these, because some of these you guys should already know. And some of these should look very familiar. So for instance, like the very, very first one, sodium azide. That's just N3. N3 minus. You know, with a little sodium, you know, kind of floating next to it. But he draws the Lewis dot structure there. That way you guys know how it's bonded and how the atoms are arranged. But this is going to be no different than the mechanisms you guys have already learned. What kind of mechanism are we doing here? Yep, standard SN2. We got ourselves a nice little aprotic solvent there. But now, it's not really that strong of a base and not really that strong of a nucleophile because we've got some what in there? Starts with an R. We got some resonance in there. We could dump those electrons onto that middle nitrogen or push it over here to middle nitrogen on this side. We could dump both bonds on the middle nitrogen. We could play around with those bonds. Not a whole lot, but we do have some resonance there. Kind of like sulfuric acid in the elimination pathway. This is going to be a very poor nucleophile. And what kind of carbon is our leaving group sitting on?
Primary.
It's on a primary carbon, right? So that immediately is going to throw the SN1 and E1 mechanism out the window before we even approach the problem. And right, because this guy is not really a strong base, not really a strong nucleophile, we're going to favor a nice SN2. We're going to come right in here, and bromine is going to leave. Now, why did I draw the arrow right there specifically? There's a reason for it. SN2 likes what kind of attack? Backside attack. So if bromine's sitting right there, we need to come in from the backside, from behind bromine. So we're not going to come in from down here. We're not coming from up top over here. We have to come in from behind bromine. But now that's going to cause some issues here. So when this guy attacks here, what happens to this methyl group? It gets pushed over here where bromine used to be. So I'm going to draw out my nitrogen here. Nitrogen is attached, and methyl has now been pushed over. Positive charge here, lone pair, lone pair, lone pair, negative charge. And then what about that, what about the other two? What about that hydrogen? Is it changing planes, orientations?
No.
Nope.
No. The backside attack only affects the plane of your leaving group. That hydrogen's not going anywhere. So it is going to be in the exact same orientation. And then, what about the D? What happens to it? Does it change orientation at all? No. I know, backside attack, the D, this lecture just went off into the gutter somewhere. But who can tell me what actually the D actually stands for?
Deuterium.
Deuterium, which is a what?
A very heavy.
It's just a heavy what?
Hydrogen.
It's a heavy hydrogen by 1 mass unit. And that's going to be important because we have to, guess what? What does this tell us to do? Stereochemistry, and guess what? That's the only question on here that tells you to do that. Notice how all the other ones just say, okay, we want the product. But nothing says anything about labeling some stereocenters. Not even on question 2. So don't be that person that forgets to label the one stereocenter in here. So it's going to be this guy right here in the center. But let's start numbering off our priorities. I'll use the magical red pen of priority. So who's going to be number 1 here?
Nitrogen.
Yep, N3, hands down. Nitrogen is going to take precedence over all of the other groups in here. And who takes number 2?
CH3.
Yep, that nice methyl. And then who takes number 3?
D.
The D. And then low-hanging fruit, number 4. So which direction are we counting in?
Counterclockwise.
S.
Yeah, we're counting in that S direction, but can we keep it that way?
No.
No, we switch it to R. So we got an R center. And again, this one is no different than a lot of the other SN2 reactions you guys have done. It's just N3 just looks menacing. Do I even need to show you what this is? What kind of mechanism is this?
E2.
Tertiary carbon and a strong base. What is this?
E2.
This is going to be E2. That's an E2 mechanism. We've got a strong base. That's almost as strong as they get. There's only one base stronger than that, and that is hydroxyl itself. And also, what kind of solvent is that?
It's a aprotic.
It's aprotic. You need an aprotic strong base, or strong nucleophile, in order to carry out an E2 mechanism on a tertiary carbon. Now, if you had said E1, although that would have been incorrect, your product would have still been the same, which means you could have drawn out either one of the two reactions and gotten the correct answer either way. You don't need to indicate the mechanism, you just need to indicate the product. Any questions on those first two? Anything up there still confusing to anybody? All right, now for this one, I'm not really going to go through the entire thing. I'm going to go over...
What is the significance of the BUOH? Why is that there in the first one?
Ah, good question there. So what is the significance of this? Why is butanol sitting in here? What is it behaving as, since it's underneath the arrow? It's acting as a solvent. It's an it's a protic solvent, which means we're going to be actually slowing down the SN2 mechanism. So we're almost ignoring it because it's actually slowing down our reaction. But it's just acting as a solvent. It's not reacting with anything. So we don't have to really pay too much attention to it. Good question, though. Good question. Because, yeah, butanol is kind of chilling in there, just being our nice little solvent. But, all right, now for this one, again, not going to go over the entire thing. I'm going to hit on one specific part about this, and you guys can probably already tell what it is. This. NBS coupled with, what is that? What is that following it?
Light.
Light. NBS coupled with light. Now, a lot of you guys probably just looked at this and are like, okay, well, look at step 2. There's a magnesium in there. So that means we basically made a Grignard from this. But now, we have to understand where the bromine is going to come from. Now, NBS, that stands for nitrobromosuccinimide, which is this guy. That's NBS. Now, its structure, not very important. What is important, though, is that it is a donor of a single bromine. Now, when we added Br2 with light, what happened there? What was the first thing that happened? That happened only a few times.
Two radicals. Formed radicals.
We made some radicals, right? Adding light to this does the exact same thing. Only you get the succinimide radical and a bromine radical. And what happens here is that a single bromine ends up attaching to your molecule. And that's what NBS is used for. It's used to attach a single bromine onto your molecule. And that will set us up very nicely for that second step, which is the addition of the magnesium. But now, of course, the big question is, though, how do we know where to put that bromine? So we got some options. We could put it on one of these primary ones that are out here. We could put it on this tertiary one. We got a quaternary carbon down here. Where do you guys think it's going to go? Yep, that's right. It's going to go right here. Onto that X marks the spot, that tertiary carbon. Because when we make a radical here, we're going to be left with that nice, that radical intermediate. Now I'm drawing 3 radicals in 3 different places. Now, what's wrong with this one?
1, 2, 3, 4. It's fulfilled.
Right. We can't even put a radical at that carbon in the first place. So that option's out the window. So now we have to compare the stability between the primary and tertiary. Who wins?
Tertiary.
Tertiary does. So that tertiary radical intermediate is going to be favored, and that's where we're going to stick our 1 bromine. And then again, the addition of magnesium makes it a Grignard, and then guess what? We had a ketone and some water. We're making a nice Christmas tree at the end of the molecule. We end up with this entire carbon chain attaching to the ketone itself, and we get a nice alcohol at the end. So again, the only thing I want to really hit there was what MBS is and what it does. It is a wonderful source of a single bromine, but because it's pain in the ass nature, it literally is BS. Nobody likes this molecule. It is not fun to work with. Doesn't ever want to cooperate, but it's a good source of a single bromine to make sure you only get 1 bromine attached to your molecule and not 2 or 3. But and now for the one that, like I said, my former SI instructor decided to give up on showing everyone. Literally gave up on explaining this reverse one that's right here. Because she felt like it wasn't really necessary. Like literally, I can quote her on this. She'd basically tell everybody, you know what? This is worth 27, this is maybe worth 3, just eat the points and just get everything else. That was her mentality behind this one. And I'm like, hell no. We're going to go over this one. But this one shouldn't be all that bad. This one you can work backwards from. So let's start working backwards. Let's pretend we never added H3O+. Let's get this out of here. So what never happened? The alcohol never got made, so we can just scribble out the hydrogen. And now let's undo the addition of the Grignard, right? That's this guy. So if we undo the addition of the Grignard, right, these electrons never got pushed up, which means he never attached. So our final product, or should I say our starting material, since we're going backwards, is this guy. Yeah, see how we can get that?
That makes
Not too bad, right? Like I said, she gave up on explaining this one, but I don't feel like it's that terribly complicated. Especially with Grignards. Grignards, you're just undoing the addition of H3O+, and now we're going to undo the addition of this Grignard. So we find the carbon chain in our final product, detach it, and then drop the electrons back down to go back to the original starting material, which in this case was a nice little ketone there. Do you guys have any questions on that one? That one kind of stumps a lot of students for some reason, because we're going backwards. But if you understand the reaction forward, you can dissect it and work backwards. And we know what that is. It's a frickin' E1. It's a frickin' E1. So if your gas sends some heat, there's a hydroxyl sitting right there. That is E1 all day. What about this? What about this guy?
Isn't that also like PCC?
Yeah, fun stuff, right? We have sodium hydride and then DMF. What does DMF stand for? I heard half of it. I heard the dimethyl part. That's the DM part. But what's the F stand for?
Furan.
It's not fluorine. Come on.
Furan.
Yep. Dimethylfuran. Right. Now, dimethylfuran is going to be acting as a what here? What is it doing? It's technically here to troll you guys, because DMF is an ether. It is sitting here acting solely as a solvent. So guess what? We can just scribble it out, because it is not having anything to do with this reaction. It's not reacting with anything. The big player here is that sodium hydride. So what do we get when sodium hydride breaks up in solution?
H-.
Yep. We get the useless sodium plus, and we get that oh so sweet H minus. Now, what is that H minus going to do?
Take hydrogen off of the oxygen.
Yeah, I'm hearing a series of options here. So I'm hearing attack the proton on the alcohol, and also I'm hearing it attack here and kick bromine off, because bromine's a good leaving group. Let's carry out each one of these potential options. Now, bromine is a good leaving group, but now, is a lonely hydrogen going to be strong enough to kick bromine off of there? Nope. So we're not going to attack there. Even though we have a leaving group sitting there, we're not going to be able to attack there with H-. And for those of you who said it attacks the proton in alcohol, that's right. It's going to come over here and attack that proton off the alcohol in